Welcome to this NPTEL lectures on robotics, basic and advanced concepts. In these lectures, we are looking at wheeled mobile robots. In the first lecture, I had looked at a wheeled mobile robot moving on a flat terrain. In the second lecture, we had looked at how to model a wheeled mobile robot moving on an uneven terrain. In this lecture, we look at the kinematics and dynamics of a wheeled mobile robot on uneven terrain. Okay, so the contents of this lecture are the following. We will look at the kinematic analysis of a three-wheeled mobile robot. Okay, we'll look at the solution of the direct kinematics problem. We look at the solution of the inverse kinematics problem. Then we look at the formulation of equations of motion for dynamic analysis. Then I will present some simulation results, and then I will look at the stability of a three-wheeled mobile robot on uneven terrain. Okay. So as I had mentioned in the last lecture, we will model a wheeled mobile robot as an instantaneous parallel manipulator. So we have a top platform, and although we don't have a fixed platform, but we have these three ground contact points, and we will represent these ground contact points as 3 degrees of freedom non-holonomic joints. Okay, so in a sense, G1, G2, G3 determine the fixed base, fixed in quote unquote. As the wheel mobile robot moves, this G1, G2, G3 will change with respect to the reference coordinate system, which is 0. Okay, and then there are these two rotary joints in each leg. So one rotary joint allows lateral tilting. One rotary joint represents the rotation of the wheel. In the front wheel, there is no lateral tilting, but there is steering. Okay, so phi 3 is the steering. Delta 1 and delta 2 are the lateral tilt, and theta 1, theta 2, theta 3 are the three rotations of the wheel. Okay, so as I said, we are going to look at this wheeled mobile robot as an instantaneous parallel manipulator with the platform connected to the ground by three serial chains. There are three actuated joints, which are theta 1, theta 2, and phi 3. So the theta 1 and theta 2 are the two rear wheel rotations. So you can think of some motors, maybe a hub motor, which is rotating the wheels, and wheel steering is in the front wheel, which is phi 3. And then there are these three passive joints. One of them is the wheel rotation of the front wheel, and then there are these two rear wheel tilts denoted by delta 1 and delta 2. So we are going to analyze the WMR as a parallel manipulator at every instant. Why? Because the ground contact point G1, G2, G3 are changing. So the instantaneously, we are going to think of it as a parallel robot. So the wheels are not fixed as in a parallel robot. Okay, in a typical, say, 3 RPS robot or some other Stewart curve platform, the base points are fixed with respect to the reference coordinate system. In this case, the base points are moving. But at each instant, it looks like a parallel robot. We have non-holonomic, no-slip constraints, and hence the kinematics is in terms of joint rates. Remember, we have said Vx equal to 0, Vy equal to 0, and Vz is 0 because the wheels cannot lift off from the ground, from the contact points. So the kinematics are basically in terms of the rate of change of these generalized coordinates. In the direct kinematics problem, we are given the actuation rates, which are theta 1 dot, theta 2 dot, and phi 3 dot. Theta 1 dot and theta 2 dot are in the two rear wheels. Phi 3 dot is the steering. We are also given the terrain and the WMR geometry. We want to find the orientation of the top platform, okay, and the position vector of the center of the platform. Okay, so we want to find the orientation of this top platform and the position of this top platform with respect to a fixed coordinate system. We are given theta 1 dot, theta 2 dot, and phi 3 dot. In the inverse kinematics, we are given the geometry of the wheel mobile robot, the terrain, and given any three of Vx, Vy, Vz, okay, and omega x, omega y, omega z. We know that it has 3 degrees of freedom. Remember, this is a 3 degree of freedom model. So we can only give 3 of these 6 quantities, 3 of these 6 linear velocity and angular velocity combined. And the goal is to find the rear wheel actuator inputs, theta 1 dot, theta 2 dot, and the steering input to the front wheel. Okay, so this is how the direct and inverse kinematics problems are defined. And as I mentioned, since the constraints are in terms of non-holonomic constraints, we need to derive this direct and inverse kinematics in terms of velocities. So what is the algorithm? The first step is, of course, to generate the uneven terrain surface. Okay, you have to tell me what is the uneven terrain. So we can use either bicubic patches or B-splines to reconstruct the surface from elevation data. So somebody has given you some points. What is the location of the point in X and Y and the height? We can use this elevation data to obtain the equation of a surface. Once we find the equations of the surface, we can find the metric, the curvature form, and the torsion for the ground and the wheels at the 3 wheel ground contact points. So at every point, wherever there is contact, we find this metric K and T because that is required in the contact equations. Then we form the contact equations. So for each wheel, obtain 5 ordinary differential equations in Ui dot, Vi dot, Ug dot, Vg dot, and Psi dot. Remember, we derived those contact equations, okay, in the derivatives of U, V, and Psi dots. For no slip, we set Vx and Vy to be 0, and we compute omega x, omega y, omega z as they are related to the angular velocity of the platform. So which is omega px, omega py, omega pz, and the input and passive joint rates. So the angular velocity omega x, omega y, omega z, which appear in the contact equations, can be related to the angular velocity of the platform plus the angular velocity of the inputs. So again, the inputs are theta 1 dot, theta 2 dot, and the phi dot steering. Above equation couples all 5 sets of ODEs. So for each wheel, there are 5 ODEs. This equation couples all the 5 sets of ODEs, and we are resulting in 15 ODEs in 25 variables. So we have 15 contact variables. Remember UI, VI, UGI, VGI, and Psi I into 15 contact variables. And then we have this theta 1, theta 2, theta 3, delta 1, delta 2, and phi 3. Okay, out of these 21 variables, theta 1, theta 2, and phi 3 are actuated and known. Okay, so we have 15 contact variables plus 6 from the WMR itself. But out of these 6, 3 are known. So we need 3 constraint equations. Okay, we have 21 variables, 3 are known, but we have only 15 ODEs. Okay, so we obtain the angular and linear velocity of the center of the platform. So let's assume some gamma, beta, alpha is some z, y, x Euler angle representation of the orientation of the top platform. Then the omega px, omega py, omega pz, which is nothing but the platform angular velocity along x, y, and z, will be related to alpha dot cos beta, cos gamma, minus beta dot sine gamma. Okay, we have done this earlier. We have seen how we can take simple rotations about z, y, and x, multiply these 3 rotation matrices, get a rotation matrix, and then do r dot r transpose to obtain the angular velocity of the top platform. Okay, we are doing exactly the same thing, and it turns out that we will get alpha dot, beta dot, gamma dot in some particular way. And clearly these are related to all the 15 joint variables. Okay, UI, VI, UGI, VGI for each of the wheels and their derivatives. Okay, if XC, YC, and ZC denote the coordinates of the center of the top platform in reference coordinate system 0, okay, then the linear velocity of the center of the platform is given by derivative of XC, YC, ZC, and this can be obtained as linear velocity of the wheel coordinate system. Remember, there is a wheel coordinate system for each wheel at the center of the wheel, and into omega cross the distance between to the CG of the wheel. Okay, so PCI locates the attachment of the wheel to the platform from the center of the platform, and 0 v omega I is the velocity of the center of the wheel. So CI is not the CG, it is the location of the point of attachment of the wheel to the platform. Okay, later on we will also need the velocity of the CG and location of the CG. We'll come to that. We form these holonomic constraint equations. What do we mean by holonomic? They are not related to the derivatives of the generalized coordinates. So basically, what are these three holonomic constraint equations? That the distance between C1, C2, C3 must remain constant because the top platform is rigid. Okay, so PC1 minus PC2 squared is L12 squared, and so on. So PCI leading superscript 0 for I equals 1, 2, 3 locates C1, C2, C3 from the origin of the reference coordinate system. And Lij is the distance between the centers of the wheel I and J. Okay, so these holonomic constraints are very similar to SS joint constraints. So let's look at this constraint once more. So I have C1 to C2, the distance will be constant. C1 to C3, the distance will be constant. C3 to C2, the distance will be constant because otherwise the platform is not rigid. Okay, so now we can write the algorithm how to solve the direct kinematics problem. So first is from steps 1, 2, and 4, we have 15 ODEs plus 3 algebraic equations, 3 holonomic constraints in 21 variables. There are 18 unknown variables. Why? Because theta1 dot, theta2 dot, and phi3 dot, they are the rotations of the two rear wheels and the steering of the front wheels are given. So we differentiate the holonomic constraints, convert to a system of 18 ODEs in 21 variables, out of which 3 variables are known. And we solve these equations using a ODE solver. We integrate with a ODE solver with initial conditions. And then we obtain all these 15 variables, UI, VI, WI, and so on, all these locations of each wheel, and every parameter is known, and obtain the position vector of the center and orientation of the platform from the 21 variables at each instant of time. Remember, at each instant of time, the ground contact point is changing. How about the inverse kinematics problem? We do steps 1 to 4 again. We have 21 ODEs plus 3 algebraic constraints. We assume that the linear velocity of the platform x dot, y dot, and the angular velocity about the vertical gamma dot are given. So we have 24 unknowns. Again, convert the DAs into ODEs. Now we have a set of 24 ODEs required with theta 1, theta 2, phi 3 as a function of time. Okay, so we solve this 24 ODEs and obtain theta 1, theta 2, and phi 3 as a function of time. In the direct kinematics, we had 18 ODEs. In the inverse kinematics, we have 24 ODEs. Why? Because there is a differential equation for the 6 degrees of freedom of the top platform, which is appearing. Again, The initial conditions for the direct and inverse kinematics problem must satisfy the holonomic and non-holonomic constraints. Okay, we cannot arbitrarily choose all these generalized coordinates, initial conditions. They must satisfy all the constraints. So let's look at some numerical simulation results for direct kinematics. We have geometry of the WMR. Length of the rear axle is 1 meter. Distance of the center of the front wheel from the middle of the rear axle is 1 meter. So two rear axles 1 meter. Center point of the axle to the front axle to the front wheel is also 1 meter. Torus shaped wheels are similar to what we have done earlier. R1, the small radius is 0.05 meters. R2 is 0.25 meters. And WMR center is at the centroid of the triangular top platform. Okay. We choose a set of initial conditions. So U1 is 1.5816, V1 is 3.35 by 2, and so on. So these tell you where the point of contact is initially between the three wheels and the ground, and what is the location of the x-axis between each wheel, ground contact point, the angle psi, and also all the tilt angles. Okay, these sets of values of initial condition, okay, so U1, V1, UG1, VG1, psi1, U2, V2, and so on, they are checked to satisfy the constraints. Okay, these initial values must satisfy the initial constraints, which are holonomic and non-holonomic constraints. We have actuator inputs, which was theta dot 1 dot is minus 1 radian per second, theta 2 dot is minus 0.9 radian per second, and phi 3 dot is some 0.05 t. These are chosen arbitrarily. We could have chosen some other rotation rates at the rear wheels and the steering rotation rate. Okay, so this uneven surface is same as the one which is used for single wheel dynamic simulation. So we have these simulation results. Okay, so wheel 1, the dark line shows the wheel ground contact point of the wheel 1 and 2 and 3. The bigger dash lines shows the wheel center, and the dot dash lines shows the center of the platform. Okay, so since these wheels are moving on uneven terrain, all these curves will look different because the wheels are tilting. Okay, so as you can see, the center of the platform is this line. The wheel 3 looks like this, and the wheel ground contact point looks like this. Okay, wheel 2 and wheel 1, the wheel ground contact point and the motion of the wheel centers are different. We can also find delta 1 and delta 2, which are the lateral tilt of the two rear wheels. So as you can see, the delta 1 and delta 2 are adjusting in a way, or they are behaving in a way such that Vx, Vy is 0. There is no slip at the wheel ground contact points. Okay, so the locus of wheel centers not the same as wheel ground contact point. This is uneven terrain and there is lateral tilt. The lateral tilt changes at different points of the uneven terrain, which is expected. Okay, due to the uneven terrain, the distance between the two contact points in the rear wheel will be different at different instants of time, and hence the lateral tilt will be different. We can also plot and see whether the constraints are satisfied during the simulation. These are the three holonomic constraints. So basically the distance between C1, C2, C2, C3 and C3, C1 are constant. We can also plot the slip velocities, which is Vx and Vy. So as you can see, all of them are more or less satisfied. Okay, so we have very small constraints violation, we also have very small slip velocities. Okay, the holonomic constraints are satisfied up to 10 minus 7 meters. There is virtually no slip. The WMR traverses uneven terrain without slip. This is a video showing the direct kinematics of the three-wheeled robot, and I will show that at the end. Okay, I will show it with some other videos. Okay, basically this is the surface, and this yellow, green and red are the three wheels, and you will see in the video that it can go over this uneven terrain. We can also do the inverse kinematic simulations. Okay, again the geometry of the WMR is same as used in the direct kinematics. Basically the length of the rear axle is 1 meter. The distance of from the center of the front wheel to the middle of the rear axle is 1 meter. Torus shaped wheels R1 is 0.05, R2 is 0.25. WMR center is at the center of the triangular platform. Again, we choose these initial conditions to satisfy the constraints. Okay, so I'm not going to go into each and every term, but we have obtained U1, V1, U2, V2, UG1, VG1, and so on, everything such that they satisfy the constraints. The inputs are XC dot is 0.03 meters per second, YC dot is 0.15 meters per second, and gamma dot is minus 0.005 t radians per second. So I want a velocity along the x direction, x component velocity as 0.03 meters per second. The y component of the center of the top platform should have a 0.15 meters per second, and it should rotate by some 0.05 into t radians per second. The uneven surface is same as used in direct kinematics. Okay, again we can plot the wheel ground contact point, which is the dark line, the center of the platform, which is the dot dash line, which is seen here, and the wheel center. So for the three wheels, so this is one wheel, this is another wheel, this is the front wheel, and this is the platform center. You can plot the trajectory of all these points. Okay. Likewise, you can find the plot of delta 1 and delta 2, which are the lateral tilts. So again, due to uneven terrain, locus of wheel center are not same as wheel ground contact point. Okay. If the wheel was rolling on a flat terrain, straight or taking a turn, okay, the wheel center and the contact point should be on top of each other. Okay, and if you are looking from the top, they should be along the same trajectory. Again, the lateral tilt changes at different points of the uneven terrain, as expected. We can also plot the constraints as a function of time. We can plot the constraints between C1 and C2, C2 and C3, and C1 and C3, the distance. And we can see that it is very small. It is of the order of 10 minus 7. We can also plot the slip velocities. Okay, the slip velocity at the three wheel ground contact points. So this is for one wheel, this is for another wheel, this is for the third wheel, and we are plotting Vx and Vy. All of them are very, very close to 0. It is like 10 minus 16. Okay. So the holonomic constraints are satisfied up to 10 minus 7 meters. There is virtually no slip. The WMR is traversing this uneven terrain without slip, okay, which is what we wanted. Remember, as I said, that on an uneven terrain, if the axle length is constant, okay, then the wheels will slip. However, we have proposed a way of letting this torus-shaped wheel tilt laterally, and the distance between the wheel ground contact points of the two rear wheels will adjust such that there is no slip. And this is a proof by simulation. Let's continue. We can also perform the dynamic analysis of this WMR. We can derive the equation of motion for the WMR using the Lagrangian formulation. Okay, the kinetic energy of the wheels, platform and links connecting the actuated and passive joints to the platform need to be computed. The potential energy is due to gravity. Again, in the dynamic analysis, we have 15 contact variables of the 3 wheel ground contact points, 3 passive variables and 3 actuated variables, and 6 variables for the position and orientation of the WMR platform. So totally there are 27 generalized coordinates. There are 3 actuating torques, 2 in the rear wheel and 1 for the front wheel steering. So we need 24 independent constraint equations for the system to be well pulsed. We have 27 generalized coordinates, 3 are given, so we need 24 constraint equations. So as you can see, this is a very, very complex system. We have large number of differential equations. We also have large number of constraints. So we can derive these equations of motion subjected to the holonomic and non-holonomic constraints using the Lagrangian formulation. Okay, this was done. Okay, just to give you an idea how complicated it is. The kinetic energy is kinetic energy of wheel 1, wheel 2, wheel 3, kinetic energy of the platform, kinetic energy of the links of the actuator, kinetic energy of the links also. We also have potential energy of wheel 1, wheel 2, wheel 3, platform, actuator and links. Okay, so all the kinetic energy and potential energy can be found. Okay, it's a huge, humongous task. It is very laborious and long, but nevertheless it can be found. The ideas are very simple. Kinetic energy is half I omega squared plus half mvc squared, and potential energy is like mgh. We can also find the constraint equations from inverse kinematics, which is psi q dot equal to 0, where psi is a 24 by 27 matrix. And hence, eventually, we have a set of differential equations, which are 27 of them. So the mass matrix is 27 by 27. Coriolis term is 27 by 1, gravity term. Then there are these torques, and then there is this psi transpose lambda. So these are the constraint equations, and lambdas are the Lagrange multipliers. Okay, so only 3 out of these 27 elements in this tau are non-zero. Okay, so the ones corresponding to theta 1, theta 2 and phi 3 are non-zero because they are given. All others are 0. There are no torques corresponding to the other generalized coordinates. So lambda is a 24 by 1 vector of Lagrange multipliers. We can solve for lambda. Finally, we obtain a set of 27 second order ODEs, and these were obtained in a symbolic form by using Mathematica. It took a lot of time. It is huge and humongous set of simplifications and equations which were used to obtain these 27 second order ODEs. With actuators locked and wheel tilted, WMR falls under its own weight. Okay, because this is to do with non-holonomic constraints. Okay, contrary to a normal parallel manipulator, if you lock the actuated joints, it becomes a structure. In the case of a 3 degree of freedom WMR, because the constraints at the wheel ground contact points are non-holonomic, basically they restrict the velocities, but they do not restrict the configuration of the whole parallel manipulator. And as a result, the whole platform manipulator will fall. Okay, and this was seen during simulations. So as I said, this is only because the wheel ground contact points are instantaneous 3 degrees of freedom joints. They are not like spherical joints. And there is something called form closure which is not present. Okay, we need additional terms modeling a torsion spring and a damper to prevent the top platform falling under own weight with actuators locked. And hence, this is added. So we add a corresponding to the lateral tilts some torque, which is K times delta I and Kd times delta I dot. So there is a damping and there is a spring stiffness added to the lateral tilt. Okay, so these are some constants. So this is added in a way so that it does not fall on its own weight. So here is the algorithm to do the dynamic analysis of a three-wheeled mobile robot going over uneven terrain with wheels modeled as torus shaped wheels, and also the wheel ground contact does not have slip. So first, just like kinematics, we generate the surface, we reconstruct the surface from elevation data, we find the derivatives of the surface. We need C3 continuity because we need to go to dynamics. We have the derivatives of many of these terms. We used a 4th degree B-spline surface using MATLAB spline toolbox, and the surfaces were generated. We formed the equations of motion. These are 27 second order ODEs. We obtain initial conditions. The initial conditions must satisfy no slip and holonomic constraints. The 3 actuated variables can be chosen arbitrarily. The rest 24 are obtained using inverse kinematics equation. Okay, so to obtain the initial conditions, we need to solve the inverse kinematic equations. And then we solve all these ODEs numerically in MATLAB to find how the generalized coordinates are changing in time. So a few numerical simulation results. So this is the three-wheeled mobile platform. Again, this is the model. G1, G2, G3 are the 3 non-holonomic contact points. There are 15 variables at each in these 3, 5 in each. Then there is theta 2, delta 2, theta 3, phi 3, theta 1, delta 1. And then there are the 6 variables of the top platform. Okay, this is a surface which was used earlier also, and we are going to use the same synthetically generated surface with C3 continuity for simulation. Okay, this is not a real surface. This is generated in MATLAB. The mass of the top platform is assumed to be about 10 kgs, mass of wheel 1 kg, because in dynamics we need to know masses. The allowable deflections due to lateral tilt is pi by 4, because we need to assume some spring constant in the to prevent lateral tilt beyond pi by 4 radians. And it turns out KSI is 16.24 Newton meter per radian and KDI was 0.57 Newton meter second per radian. Okay, so this is KSI is obtained for self weight and KDI is chosen such that there is some damping. The initial conditions are again obtained such that it satisfies the loop closure of the constraint equations, both the holonomic and non-holonomic constraint equations. Okay, all the initial values of the first derivatives are chosen to be 0. So this robot or this wheel-molded robot is starting from rest, and we have arbitrarily chosen tau 1 as 0.35 Newton meters, tau 2 as minus 0.5 Newton meter, tau 1 is also minus 0.35 Newton meter, and tau 3 is minus 0.01 times t. Okay, so it is tracking some trajectory. The steering there is as a function of time. Okay, we can choose other values. This was chosen by the student. So we can solve these 27 ODEs, and then we can plot what the wheel 1 is doing, what the wheel 2 is doing, and what the wheel 3 is doing. So wheel 1, wheel 2, and wheel 3. Wheel 3 is the steering wheel. We can also see what the center of the platform is doing, again using this dot dash line. At the center of the wheel, okay, and the wheel ground contact points are again different, basically because it is moving on uneven terrain. There is also delta 1 and delta 2 which is tilting. Okay, the two rear wheels are tilting so that there is no slip, and we can plot delta 1 and delta 2 as a function of time. Okay, so coming back to it, delta 1 and delta 2 are passive. Okay, so they vary or adjust automatically to avoid slip. We can see that the error in the holonomic constraints are very small, of the order of 10 minus 6. So this is the constraint between C1 and C2. This is the constraint between C1 and C3, and this dot dash is the constraint between 2 and 3. As you can see, it is very small. It is 10 minus 6. We can also check Vx and Vy for the slip velocity at all the three wheels, okay, at the wheel ground contact point. And as you can see, they are also very small. This dashed line is for Vy, Vx is the solid line. They are all like 10 minus 7, of the order of 10 minus 7. Okay, so all the constraints are satisfied at least up to 10 minus 7. Okay, distance meters, and this is something else, velocities. The three-wheel mobile robot can hence to be shown to travel an uneven terrain without slip, because the slips are so small, the constraints are satisfied, and as you can see, it is tracing some path on the uneven terrain. Okay, so next let's look at stability of this three-wheel mobile robot on uneven terrain. Okay, so on an uneven terrain, the loss of vehicle stability could be due to tip over or roll over. Okay, tip over means the vehicle undergoes rotation, resulting in reduction in the number of vehicle ground contact points. Okay, so instead of 3, you can have less. Mobility is lost, and if the rotational motion during tip over is not arrested, the vehicle will overturn. So first thing is, we need to find or define a measure of stability to warn the operator, or if you are on the vehicle, to see that it is tipping over or it's about to tip over. Okay, like in any vehicle, the placement of the center of mass, speed, acceleration, external forces and moments, and the nature of terrain will determine the tip over or stability. Okay, it is not only one parameter. Various parameters are involved to obtain the stability of a mobile robot on uneven terrain. There are various measures of stability which has been developed. Okay, we are going to use something called the force angle stability measure. This was first developed in '96. Okay, and we will investigate the stability of the previously developed three-wheeled mobile robot with torus-shaped wheels for different conditions. So what is the force angle stability measure? Okay, so let us look at a center of mass which is subjected to a force Fr. Okay, so this is the center of mass of the platform. There is a force which is acting. This is the terrain. Okay, the Fr makes an angle θ1 and θ2 with the tip over axis normals I1 and I2. Okay, so these are the two wheels. There are these axis normals I1 and I2. Okay, and it makes an angle θ1 and θ2. So θ1 and θ2. The force angle stability measure tells you that this variable psi, okay, which is minimum of θ1, θ2 into Fr. Okay, so this psi should have some range of values. So basically what it eventually will boil down to the fact is that this Fr should not be, these angles θ1 and θ2 should not be such that this Fr is outside these I1 and I2, roughly speaking. Okay, and we have this reference coordinate system xy, and we can locate the point of contact, which is P1 in this case, and we can also locate the center of the platform, which is PC. So in the case of a three-wheeled mobile robot, so we have wheel 1, wheel 2, wheel 3. We can locate the wheel ground contact points by UG, VG, and Z, okay, for each of the three wheels. The location of the center of mass, PC, is XC, YC, ZC. The line joining the wheel ground contact points is AI. So A3 is the line which joins wheel 1 to wheel 3. A2 is between 2 and 3, and A1 is between, A1 is between wheel 1 and wheel 3. And then we have this force which is acting at the center of mass, which is Fr. Okay. So the component of the net resultant force is F2 star. Okay, for tip over axis A2. So the angle θ2 for the tip over axis A2. Likewise, we find θ1 for A1 and θ3 for A3. So there are these three angles which tells you the angle between the normal I1, I2, I3 and the resultant force F2 star. Okay, this is for A2, similarly for F1 star and F2 star. So if any theta I is 0, the omega r can tip over AI. Okay, so basically what is happening? So if this θ2 is 0, so which means what? F2 star is along this normal I2. So both now the WMR can tip over A2 about this wheel. Okay, so that is the basic idea. We will calculate these angles and make sure they are not 0. If they are coming close to 0, we know that tip over about a certain line is going to occur. Okay. The net resultant force can be computed also. So this Fr is given by the force due to gravity, the force due to disturbance, minus the force due to the inertia. Okay. So force due to gravity and inertia are obtained from dynamic simulation. The F disturbance is some external disturbance which we need to assume. The net resultant moment at the center of mass is due to gravity, the disturbance moment and the inertial moment. We are interested in component of Fi and Ni about the tip over axis AI. Okay. So there are three of them between 1 and 2, 2 and 3, and 2 and so 1, 2, 2, 3, 3 and 1. It can tip over any one of these axes. So we want to find the force for that tip over axis and also the angle. So we know this Fi and Ni about the tip over axis. We have to combine this Fi and Ni to get a resultant force, which is this Fi star, and this is combined in this way. So Fi star is Fi plus the normal II cross Ni divided by the magnitude of II. So II is the tip over axis normal. Okay. So from the dynamic simulation, we will get some force Fi and Ni. We need to combine them to find the resultant force, which is given in this form, and then we compute the angle stability measure θi, which is the angle between Fi star and the unit vector along the normal II. Okay, the sign of θi determines if the net resultant force is inside the support polygon or not, and the overall force angle stability measure states is that this is psi I, which is the minimum of all three. So it can tip over any one of these three axes. So we need to find the minimum of θ1, θ2, θ3, and then take a decision about which axis it is going to tip over. So let's look at some numerical simulations. So again, the mass of the top platform is 10 kg. We are going to use the same numbers as used in dynamic analysis. Mass of each wheel is 1 kg. The spring constant, we have assumed some springs to prevent lateral tilting, and the damping is this. We look at various terrains. We can look at a curved path on a flat terrain, two rear wheels on two different planes, and uneven terrains. For each of the chosen path and our input torques, compute at every instant of time the net resultant force which is acting at the center of mass, the net resultant moment NR which is acting at the center of mass, compute the tip over axis AI and the normal I at each one of these contact points, I equals 1, 2 and 3. Compute Fi star by combining Fr and Nr, and then you compute the force angle stability measure. Okay, this should be away from 0. It should be for minimum of theta 1, theta 2, theta 3 should be away from 0. So here is a simulation of a wheeled mobile robot, okay, which is traveling on a trajectory on a flat surface. Okay, so the wheel 3 is this dark line. The projection of this resultant force F star is this dashed line, which is this one. Okay, wheel 1 is this dot dash line, and the wheel 2 is this one. Okay, so what you can see is that force angle stability measure, basically the angle behaves like this, and then it comes down to about 0.6. Okay, so as the WMR turns, the stability margin reduces, but it is all still stable. It never goes towards 0. And in this example, we have assumed torques as tau 1 is 0.5, minus 0.5, tau 2 is minus 0.75, and tau 3 to trace this circle is minus 0.0404 t. Okay, so basically what have we done? Let's summarize. I have the equations of motion. I can solve the equations of motion to find out what is the net resultant force and the net resultant moment acting at the CG of the top platform. Then I can find this tip over axis between A1, A2 and A3. Okay, 3 of those between wheels 1 and 2, 2 and 3 and 3 and 1. Then I can find the normals, and then I can find the angle between this resultant force and this I1, I2, I3, and then plot all of them, evaluate all of them, and show how the wheel is moving on this flat terrain. I can show this is the third wheel, these are the first 1 and 2 wheels, and this is the projection of the force vector onto the plane. And then I can compute this theta, theta 1, theta 2, theta 3, and the minimum of those, and plot it. Okay, so what does it say? That it is reasonably stable. It is this wheeled mobile robot can move on a flat terrain in a stable manner. When it is turning, the stability margin reduces a little bit, but nevertheless it's fine. Now let's look at this wheeled mobile robot on an inclined plane. So again, basically I can plot what the first wheel is doing, the second wheel is doing, and the third wheel is doing. Okay, so what we can see here is the stability margin to slip at wheel 1, which is this dashed lines 1, 2 and 3, and this is the holonomic constraint. So all of them are very close to 0. Remember, they are like 10 minus 7. So the stability margin here is also away from 0. Okay, so this wheeled mobile robot on this inclined terrain is still stable for these kinds of inputs again. Okay, tau 1 is minus 2.4, tau 2 is minus 4, and tau 3 is 0.08 t. Okay. Initially, it is least stable about axis 2. As the WMR wants, the tip over starts shifting from axis 2 to 1, and stability increases. Okay. Now let's look at a wheeled mobile robot on an uneven terrain, which looks like this. So there is a hump here, and we want this wheeled mobile robot to go over this hump. Okay, so what you can see is the first wheel looks like this. This is the path it traverses. The second wheel looks like this, and the third wheel is at the middle. Okay, again the input torques at tau 1 is -4, tau 2 is -4.0, and tau 3 there is no steering, it is going straight over this uneven terrain. We have just chosen arbitrarily some numbers to try out different cases. We have tried many cases. Okay, and again the stability margins 1, 2 and the z component of this motion is plotted here. So what you can see is the stability margin 1 and 2, they are all away from 0. Okay, and the WMR is able to negotiate this hump, which is an obstacle on uneven terrain, without tip over. Let's try another trajectory where the surface is slightly different. So again, we have 1 which is wheel 1, 2 which is wheel 2, 3 which is wheel 3, and at 4 there is unstable behavior that is happening, which is shown here. So let's go back a little bit. Again, we are applying some torque, tau 1 -4, tau 2 -4, and tau 3 is 0. There is no steering. Okay. The stability margin reduces while climbing the second peak, not this first one, the second peak, and tip over occurs about axis 1. So this simulation shows that after some time, this at this 8 point something, the stability margin is going below 0. So there is not much meaning what is happening here. Okay. Also, the wheel slip is also increasing a lot. So after some point, there is wheel slip. So again, there is no point in simulation. Nevertheless, what it is showing here is that the stability margin is going below 0 and hence there is a tip over. So in summary, a 3-wheel mobile robot with torus-shaped wheels was studied for stability. The rear wheels with passive lateral tilt capability are present. We modeled this 3-wheel mobile robot as a parallel robot with 3 degrees of freedom. The solution of the direct and inverse kinematics was obtained by integration, because the direct and inverse kinematics are related to the velocities, unlike in a serial robot. I showed you some dynamic modeling and simulation. I will show you next also some more dynamic modeling and simulation using a software package called Adams after this. Okay, so in Adams, I don't have to do all these things in MATLAB. So, and do all this 27 equations and 24 equations. So we can make a CAD model of the 3-wheel mobile robot. We can make a CAD model of the surface, and then we can simulate on the surface. I also showed you how we can traverse this uneven terrain without slip by allowing this lateral tilting. Finally, with force angle stability measure, I could show you that it could measure or indicate tip over stability. Okay, it's a measure of tip over stability, and I looked at several trajectories on uneven terrains, on flat terrains, on inclined planes and uneven terrains, and I showed you that we could compute this force angle stability measure, and in one of the examples I showed you that it could do tip over. Okay, so with this we'll come in the next, after this I'll show you some videos. In these set of lectures we were looking at wheeled mobile robots. In the last, I discussed and I mentioned that I'm going to show some videos of wheeled mobile robots going on uneven terrain. Okay, so the first video is on a motion of a 3-wheeled mobile robots, which was simulated using MATLAB. The uneven terrains were generated using spline toolbox in MATLAB. We solved the direct kinematics equations, which was discussed previously. We integrated the first ODEs and found all the 15 variables, wheel ground contact point, and also how the thetas and the top platform moved. Okay, and I showed you in simulation that there was very little slip and the holonomic constraints were satisfied. So this solution was generated in MATLAB, and then in MATLAB there is a feature to animate the results, and this video shows the animation. Okay, so it is looking little crude, but nevertheless, you can see that the three wheels are moving on uneven terrain. And I had actually showed you earlier plots of this direct kinematic simulation and showed that there is no slip. In the next slide, I will show you some videos obtained using something called Adams. Okay, so Adams is a commercial simulation software package. And again, we can create a model of the three-wheeled mobile robot in Adams. Okay, it's a dynamic model, meaning it solves the dynamic equations of motion in its own way. We can create the uneven terrain using a CAD model. The three-wheeled mobile robot with torus-shaped wheels was also created using CAD tools. Now, in Adams, to connect the two wheels to the body, we need to provide some kind of a suspension. Remember, the wheels can tilt laterally and it can go up and down. Okay, so we need a 2 degree of freedom suspension, and one of my students worked on this 2 degrees of freedom suspension, and we incorporated a 2 degree of freedom suspension on this wheeled mobile robot. So basically 1 degree of suspension is to allow the tilt, and 1 degree of freedom is to account for the vertical motion of the platform and the wheel. So you choose appropriate settings in Adams. Okay, so you need to play around with Adams because you need to set the friction in Adams and something called the depth of penetration of the wheels. Okay, so that is the way Adams works. Okay, you need to make sure that the wheels are always in contact with the uneven terrain by giving this depth of penetration, and also you have to specify a friction. In the MATLAB simulations, I did not specify any friction at the wheel ground contact point, okay, because that was the way it was developed. Okay, we don't need to incorporate the friction at the wheel ground contact point in MATLAB. Basically, there is no slip, so there is no friction. We also need to choose the inputs appropriately in Adams. We need to play around with it. So what you will see now is the motion of a three-wheeled mobile robot going on an uneven terrain, which was both the uneven terrain and the robot was created in CAD models, and then appropriate parameters were set, and then you can see it is moving. So the important thing to notice here is that this uneven terrain, it looks like some wavy surface because we can't generate very complicated uneven terrains in Adams. The important thing to notice is that the wheels are tilting laterally. Okay, so the front wheel is rotating and also it is being steered, whereas the two rear wheels are rotating and tilting laterally. So as you can see, the motion is quite smooth. There is almost no slip. I mean, you can't see that there is no slip in the video, but if you look at the atom simulation and you can plot all the variables again, and you can see that there is no slip. But definitely this video shows that this three-wheeled mobile robot with torus-shaped wheels and wheels capable of lateral tilting can negotiate an uneven terrain. This is another uneven terrain. and the same three-wheeled mobile robot, which is negotiating this uneven terrain. Okay, Adams is a very, very powerful commercial package. Okay, there are plugins and there are extensions of Adams which can simulate the motion of a car or a four-wheeled vehicle. Okay, it's called Adams car. Okay, but this is not using Adams car. We have just imported the surface from a CAD model. We have also imported a model of this three-wheeled vehicle. Then we have put suitable joints between this green platform and the wheels, and then we are giving some input. Okay. So this is another terrain which was created, and this is that same three-wheeled vehicle negotiating this uneven terrain. Again, I can see that there are these hills and valleys and wavy terrain, and then we can go negotiate the terrain with the wheels always in contact with the terrain. Okay, so the wheels are always in contact with the terrain. It is not floating in air, and that is the way to do that is to specify some friction and some depth of penetration. So the depth of penetration is very small. Okay, so with that, we come to an end of this set of lectures on wheeled mobile robots. Thank you for listening.